Welcome back to ECE 501B. Homework number 5 is due tomorrow evening if you want that much time. Some of you look like you've already turned it in. That's fine. I'll try to remember to take that when I leave. The next time that we are scheduled to meet won't happen physically on campus, so don't come to class on Monday expecting to see me. You can come here and sit here if you want, but I don't believe I'm going to be here. So I will try to make Monday's lecture available on the internet or on the D2L website. So you can watch it, I hope, on D2L. That's the plan. Just as a keeping us all alert, mainly maybe me, our next exam is actually 3 weeks from today. That's on the 6th of November. Homework number 6 will be due a week from today. And then we'll have some more homeworks between that homework and exam number 2. What I want to do today is continue with Chapter 6. Boy, the list just keeps growing and growing as far as what I want to cover. But the first bullet, the inner product, we've already talked about. That was last time. The inner product now, as far as we've taken it, has provided us with a norm, which is really a scalar way of representing two vectors. Or you can think of it, if you use those two vectors, if those two vectors were one and the same, now you have the length of a vector, or the square of the length of that vector. And we also talked about orthogonality. What does that mean? Well, that means the inner product of two vectors equals 0. And that's going to depend on how you've defined your inner product, what it means for two vectors, in quotes, to be orthogonal. Those vectors are anything that are in this set that we've called a vector space. Those are elements of this vector space. Those are our vectors, and they may not be these tall, thin things. They may be polynomials. They may be other items that are being called vectors. Today what we want to do is a little CSI, a little Cauchy-Schwarz inequality, which is really given in blue. The inner product, the magnitude of the inner product. So your inner product could be negative. If you take the magnitude of that inner product, it's going to have a value, and that's just a scalar. It's going to be less than or equal to the norms of those two vectors, the product of those two vectors' norms. If you rewrite that absolute value of the inequality, then you get that minus the product of those two norms is less than or equal to the inner product. That's when that inner product might be negative, so it can go all the way on the negative side, or it's bounded above by the positive side. But if you now have that same quantity, U norm, V norm, on both sides, if you divide by that, now you have a 1 on the right-hand side, you have a -1 on the left-hand side, you now have this quantity, inner product of UV over the norm of U and V. That's like the cosine of an angle theta. And you can now say, oh, those two vectors have an angle associated with them based on this formula. Take the inner product of those two vectors, and if you had two tall, thin things, you might have two vectors. You could form their inner product, divide by the norm of each of those, and then inverse cosine, and now you have an angle associated with those vectors. And you might not have vectors that are tall, thin things. They may be polynomials that are vectors. And you can now talk about the angle between those vectors. We'll then discuss or talk about the triangle inequality, the parallelogram equality, orthonormal basis, and the Gram-Schmidt orthogonalization approach. That's really just a way of creating a set of vectors or a list of vectors that are orthonormal. We'll build up a collection of orthonormal vectors or a list of those. What I thought I would do before your eyes start rolling back in your head and we talk about all these theorems and corollaries, I thought I'd try to replay quickly what we've already covered in chapter 6 so that we kind of have all of this playing in our head and we can try to keep track of it as we move forward with this crime scene investigation. With the Cauchy-Schwarz inequality. That's where we want to start. But before we start, remember the inner product. It simply takes two vectors and produces a scalar in whatever field we are playing with, the real numbers or the complex numbers. That's the result of this inner product. And the inner product has several properties associated with it. And if you're then creating an inner product, you need to make sure that each of these properties are satisfied for your inner product. One is positivity, meaning if you take the inner product with itself on a vector, that better give you a non-negative real number. That's what the greater than or equal to means. Definiteness, that means if you look at any vector v and form the inner product with itself, the only time that the inner product will give you 0 is when that vector itself is identically 0. That's the definiteness property of the inner product. Additivity in the first slot, and we'll be using these today as we move through some of these theorems and corollaries. Additivity in the first slot, that seems fairly straightforward. We just pull out the two first slot pieces and take their respective inner products. Homogeneity in the first slot, that A slides across or slides out of the inner product. If the A was in the second slot, what happens? With the A in the second slot, then that A comes out as a conjugate, doesn't it? And we're going to use that. And that's a result of this conjugate symmetry, if we wanted to sort of play it that way. Those are the properties. Then we looked at some features. We can create a norm, which is the square root of the inner product of U with itself. Here's using that first and second slot homogeneity property to derive that the norm squared of a scalar times a vector is actually going to be the absolute value of that scalar, meaning if it's a complex number, you find its magnitude and square it, and then multiply that times, whoops, wake up, the square of the norm, right? That's what the inner product with itself gives us. That gives us this norm squared. Meaning AV normed squared is just the inner product of AV with itself. We can pull out the A from the first slot. We just had that property. If we pull the A out of the second slot, the conjugate comes out of A. But now A times its conjugate simply gives us the magnitude squared of that complex number, if it's complex. If it's real, then you don't have to worry about all this conjugate stuff. Orthogonality. Two vectors, U and V, are orthogonal. That's what I'm meaning by this symbol, this upside down T. That's supposed to be an orthogonality symbol. U is orthogonal to V if their inner product is 0. And again, that depends on the inner product that we've defined. But once we've defined that inner product, now you can think about, if you have two vectors, you can decompose one of those vectors in terms of the other one. In this case, we are rewriting a vector u in two pieces. One piece is along the direction of v, the other vector, and we derived where this coefficient a, this scalar a, was coming from. That was just the inner product of u and v. That sort of tells you how strongly aligned u and v are in quotes. But if you had the inner product of u and v being 0, then you know that they are orthogonal, aren't they? And if they are closely aligned, this uv inner product is going to be large, and you'll then normalize that with v squared. And that's the amount of u in the direction of v. Then you have the orthogonal component of that decomposition. You've now taken the amount that's in line with v, and now you need to go orthogonal to that scaled location, and that will get you back to u. And we may, going forward, just say, oh, take the piece that's aligned with v and its orthogonal complement, its orthogonal component, and we may call that w, and not have to parameterize it in this way, u minus av. But that's the component of u that's perpendicular to v, is another way of thinking of it. Questions on that? That gets us now to CSI, Cauchy-Schwarz inequality. And I think we stated this last time before we left. Given two vectors that are in this vector space, capital V, then the magnitude of their inner product is less than or equal to the product of their two norms. Those norms are using or applying the inner product that we're using. You have equality between the left-hand side and the right-hand side if and only if u and v are multiples of each other, scalar multiples of each other, that they're aligned, essentially. Then you have equality. And we've also seen that if you rewrite this in a less compact manner and basically rewrite what this absolute value means, then you can rewrite your Cauchy-Schwarz inequality as being bounded between a large, I don't know how you want to say this, but a very negative value and a very positive value. That's now your inner product bound for uv. Let's now convince ourselves, which means prove this relationship. To do that, first we need to let these two vectors be in our vector space V. Now, we look at a couple of cases. If V is equal to 0, then we have that condition is true, isn't it? We have 0 is less than or equal to 0. So both sides are 0, and that's valid. So let's look at the other case where V is non-zero. If that's the case, then let's decompose U into this orthogonal decomposition. A piece of it is going to be in the direction of V, and the other piece is going to be orthogonal to V. if v is not equal to 0, we can decompose u in terms of v. And let's say w, like I said before, where w is in our vector space, but yet, what does that mean? I've introduced a third vector here, but that's the w that's actually, if its inner product is 0, w and v are orthogonal. So w is what I had written in blue before when we first started. That's the orthogonal direction of v. So we're going to decompose u into these two pieces, a piece v along v and a piece that's orthogonal to v. And that then says that we can rewrite u as the inner product of u and v over v squared. Wasn't that our a before? There is our a that we were using before, u, v inner product over v in the direction of v plus w. So that's just another way of rewriting u. But what do we know about vectors that are orthogonal to each other? And now just think of a squared plus b squared equals c squared. You know Pythagorean theorem is valid for that. And you could think of u being c, and these other two parts are a and b. I'm kind of overusing a, aren't I? A was the coefficient, so maybe I should have added those. But I hope you know what I'm trying to say. So by the Pythagorean theorem, let me not write all of that out, but by Pythagorean theorem, we now know that the norm of u squared, there's c squared, is equal to the norm of that first vector on the right-hand side, which is u v inner product over v squared v, that one squared, plus w squared. Questions on that? That's just Pythagorean theorem, isn't it? So now let's clean up that first term on the right. We can, the u v inner product over v squared, that's just a scalar. And remember how we could pull that out? We could just take that a and square it and bring it out of that inner product, which now we have the norm of v squared, which is really just an inner product of v with itself. Meaning we can now rewrite this as u v v squared. That's a. We're just going to take its magnitude and square it. And now take v inner product with itself. Plus w squared. Questions on that step? But we can rewrite v inner product with v as the norm of v squared. So that we now have, this is now the inner product of u and v squared squared. This is now v, or the norm of v squared, plus w squared. But we have several squares going on with, or we have several norms of v floating around. Let's just reduce that to one of those pieces. We have v squared, and now we have what? V squared squared. So let's just get rid of one of those. And we then end up with, how do I want to say this? Let's say this is now uv squared over v squared. And what was on the right? On the right was u squared. I'm sorry, on the left. Don't know my right from my left. I'm lecturing upside down if you aren't watching live. They'll never know, right? I'm on my head. Now what do we do? Well, we know by the positivity of the inner product that this piece, this component that's orthogonal, is positive, isn't it? It can't be negative. This is now greater than 0. By the positivity of our inner product. We know that to be true. We know the norm has to be non-negative. Well, if that's the case, why don't we throw that piece away, and then we know that the left-hand side has to be greater than or less, or greater than or equal to the right-hand side after eliminating that w squared. Meaning we can now say that u squared is greater than or equal to uv's inner product normed, absolute valued and squared v squared. Now we can multiply both sides by v squared, or the norm of v squared, and we end up then with u squared v squared greater than or equal to the inner product of u and v magnitude squared. And if we take the square root of both sides and maybe rewrite this so that it looks more like what we were starting with, we have the inner product of u with v, take its absolute value, and that's then less than or equal to the norm of u times the norm of v. Even though we used the idea of the inner product, we never had to get specific with what it looked like, did we? We just had to say there was an inner product in play and that it's defining these norms. But we in no place of this derivation had to specify what the inner product was. As long as the inner product satisfied the inner product properties, we're okay. So this required no definition or specification of the inner product. And I want you to just sort of remember that this now gives us an angle. Note, we could, and I've said this many times, but now hopefully you're okay with this equation. If we get rid of the absolute value or the magnitude of the inner product, we can now write it that way. And if we divide both sides through by the norm of u times the norm of v, then we get minus 1 is less than or equal to the inner product of u and v divided by the norm of u times the norm of v, less than or equal to 1. And this piece now, we know that the cosine of an angle is bounded between -1 and 1, so that we could sort of think of theta like an angle between these two vectors, u and v. Questions on that? So now we have CSI. I don't know how many seasons of it we have, but we have CSI, right? Cauchy-Schwarz inequality. Hopefully you're not even familiar with what I'm trying to play a joke about. It's still on the air though, isn't it? Yeah. Wow. Longevity. Now let's talk about something else, which is the triangle inequality, and that I'm just trying to orient you with where we're at in the book. That's, I think, 6.9 is the labeling that Axler uses. The triangle inequality. And if you get confused with all of these terms and definitions, just think of a triangle and say the sum of the lengths of any of those two sides has to exceed the length of the third side. And that's really all we're saying here, but now we're generalizing it to any dimension, finite dimension, and not just triangles. This says if we're given two vectors, u and v, in a vector space capital V, then the sum of two vectors, the norm of that sum, is less than or equal to the norm of u plus the norm of v. If we wanted to have equality, then what we need, wow, I don't know what happened there. We have equality if and only if u and v are non-negative scalar multiples. Basically, u and v are aligned again. So your triangle is now basically all aligned if you're thinking of a triangle. Then you can have two sides equaling the third side. But if you pull that triangle apart, that's not going to be the case. All right, let's see where this is coming from, or try to justify this by a proof. We start with the given information. U and V are in our vector space V. And a lot of times it's easier to work with the norm squared and not just the norm. What does this equal? The norm of U plus V quantity squared. That's an inner product, isn't it? So we now have the inner product of U plus V and U plus V. But that we can pull apart, can't we, or separate, because we know that additivity is okay in the first slot, and I think last time we showed that it's okay in the second slot also, didn't we? So now we can pull apart and make this into four pieces from one. The first piece, let's say, is U with U. Then maybe we're doing FOIL here. First, last, no. first? I don't know. Anyway, let's do the v with v. And then we can have the other two terms. We have u with v, and we have then v with u. So now we have u with itself, v with itself, u and v, but we can also write that as u and v conjugated by the conjugate symmetry. But now if I have a number, and these are all just scalars, aren't they, now, since they're inner products. These are just scalars. They could be complex numbers, but they're scalars. I now have a number, a complex number in general, plus its conjugate. What does that produce? It leaves us just with the real part, right? So if we had alpha plus j beta plus alpha minus j beta, we have two of the real parts left. And these first two pieces, we could just write those as norms squared. But now we have 2 times the real part of the inner product of u and v. Is that okay? But now, what I want to do is I'm trying to put an inequality in here. If this inner product of u and v is a complex number, and now it has a real part and an imaginary part, right now I just have 2's of the reals. Well, what if I took 2's of the magnitude? That would have to be bigger, or at the best equal to the real piece, right? If I didn't have an imaginary component to that. So I can now say that this right-hand side is less than or equal to the norm of u squared plus the norm of v squared plus 2 times the magnitude of the inner product of u with v. Since the magnitude of the inner product of u with v is bigger than or equal to the real part of u and v, inner product. Is that okay? I'm now going to say that that's what I have right above is less than, or what I'm going to put on the right-hand side is now bigger than the norm of u squared, the norm of v squared plus 2 times the magnitude of the inner product of u and v. So what I'm saying there is that the real part of some complex number z is less than or equal to the absolute value of z. That's what I'm saying in that step. But now what do I know? I now have a bound on the absolute value of the inner product from CSI. It's a good thing we still have the first season of CSI. Cauchy-Schwarz inequality. This is now less than or equal to u squared plus v's norm squared plus 2 times the norm of u, the norm of v. And this was I think I misspelled that. That's why I just need to abbreviate it CSI. Okay. Doesn't have a T in it, does it? Schwarz. Questions on that? And what was that bigger than? That was bigger than u plus v quantity squared. But if you look at what I have now on the right, that looks like a perfect square, doesn't it? So this is now equal to, or let's just say that that's now greater than, well, this we can now think of as u plus v squared. Rewriting it that way, now I can say then that u plus v norm squared is less than or equal to the norm of u plus the norm of v quantity squared. Or I can now take the square root of both sides and say that the norm of u plus v is less than or equal to the norm of u plus the norm of v. Again, I didn't have to define the inner product, did I? And again, if you wanted something to sort of physically think about, just draw a triangle. I started my other class this semester with drawing triangles, but there we were dealing with complex power. We had the complex power triangle. Now we just have a triangle. But it could represent a real part and an imaginary part, just like in the other class that I was lecturing to. So this is now called the triangle inequality. Meaning if I now went some direction u and then a direction v, if I just took the norm of u and the norm of v, that's going to be bigger than the norm of u plus v. Or the length of u plus v, which is what these norms are generalizing. And if I took this point right there and I smashed it down, the only way that you're going to get equality is if that highlighted point does get moved to lie on u plus v, so that u and v are aligned, aren't they? Non-negatively related to each other, scalar multiples. Triangle inequality. Well, I kind of like geometric figures. Apparently Axler does too. So the next one is the parallelogram equality. No inequality here. Parallelogram equality. And maybe it's easier to sort of, well, let me state it first and then maybe we'll draw a picture after we prove it. So let's say that we're given two vectors in V. Then we can actually say that the sum of those two vectors, their norm squared, plus the difference of those two vectors, norm squared, is equal to twice the norm of u squared plus the norm of v squared. pictorially what we're doing is if I went, let's say U here, and then V there, then if I went and produced a parallelogram, this is also U, and this is also supposed to be V. That's not a very good drawing. That's why I kind of refrain from drawing. But this is what? That's U plus V, isn't it? But what's U minus V? Well, it's the same thing as if I went over here U and there's plus V. If I went down here V, then U minus V is this length, which is really that length, that distance in red. So if you think of this as being a parallelogram, what you're saying with this theorem is that you take these four sides of the parallelogram and you take their norm and square it and add them up. That's going to be equal to the norm of the diagonals distances squared. That's what we're saying in this parallelogram equality. The norm of U plus V, that's squared, plus the norm of U minus V squared. That's equal to U squared plus U squared plus V squared plus V squared. That's what we're saying. If you have a long, thin envelope, it's not really a parallelogram, it's a rectangle, but you can sort of see Pythagorean theorem in that case, and it should make sense. A squared plus B squared is C squared. A squared plus B squared is C squared. You just do it twice. Well, now that generalizes if you sort of distort that rectangle into a parallelogram. That's what we're saying. And this doesn't have to pertain to geometric ideas. We just have to apply it with these norms. These norms are defined by a general inner product. So as long as we have an inner product with the appropriate properties, it satisfies this parallelogram equality. Believe me? All right, you need a proof. I was going to do something else with CSI, but I better leave that alone. Okay, so let's now take two vectors, U and V, in our vector space V. If we look at U plus V norm squared plus the norm of U minus V squared, in terms of inner products, that's U plus V inner product with U plus V. And it's U minus V inner product with U minus V. We now are comfortable, though, with pulling that all apart, aren't we? Because we have additivity in the first and second slot with all of these. Meaning the first inner product says that we have U with itself, we have V with itself, we have a U and a V, and we have a V with a U. But now we have four more terms from the second term up above. So we add that, we have U with U, we have a minus V with V, so we have a plus V with V. We have a minus u with v, I'm pulling out the second slot's minus sign and taking its conjugate. Since it's real, it just gives me a minus. Then I have a minus v and u. And all of those taken together says that I now have two u inner products with itself and two inner products of v with itself. And the other four terms cancel. Or this is now 2 times the norm of u squared plus the norm of v squared. And that's what we wanted to show, that that was equal to the norm squared of the diagonal entries in that parallelogram. Yes? So the let me see. So now you have u plus v. Maybe this is a poor diagram, but you should be able to show that u minus v is not the same length. No, it's not the same length. So now really distort your parallelogram and make these two sides or corners come very close to each other, and so u minus v might be very short relative to u plus v. So you don't necessarily have u plus v being the same magnitude or the same length or the same norm as u minus v. If we sketched this, well, maybe that's not very good either. I need to make my distortion in the angle, don't I? Is that better? Now you can hopefully see that u plus v is much longer in this two-dimensional picture as u minus v. So you're not necessarily adding up two things that are equal on the left, but they're norms squared. It's kind of interesting that this works out this way. But now you can amaze your friends by cutting out parallelograms and saying, oh, I bet I can tell you the length of that diagonal squared sum. You can have all sorts of party games with this, right? Oh, talk about nerdy. That's okay. It's all in fun, right? Other questions on this? Yes. So the question was, are the inner products the same as the dot product? They are if we're dealing with real inner product spaces. Then the dot product that you've grown up with since second grade or whenever you started doing dot products with vectors, the dot product is the same as the inner product. But if you start doing complex vector spaces, what did we say had to be true for the inner product? Then we take the complex conjugate of every term in the second slot when we multiply it with the first slot's coordinates. But when you don't have to worry about complex, then the inner product is equivalent to the dot product that you're used to maybe thinking about with real lines and real vectors. So they are equivalent in certain cases, but in general, no, you can't say that the dot product. The inner product is a generalization of the dot product. What we've said is that if we have these guys in, let's just say it was two-dimensional, we now have u1 v1 conjugate plus u2 v2 star. And those are the coordinates in my vectors u and v. Meaning now I'm saying that u was some u1, u2, and v was some v1, v2. That's equal to the inner or the dot product if u1 and v1 are real. If those coordinates are coming from the real numbers. Other questions? Now before, maybe I should have, before I finished up with the, I hate to cheat like this, but I'm going to. I can expand my paper so I can cut a little bit, or I can cheat. We didn't define the inner product, did we, in this parallelogram? That's what I was saying before. As long as you have a reasonable, a valid inner product, it satisfies that parallelogram equality. So this, there was no definition of the inner product. Again. And I think I tried to draw the parallelogram up here. So this is now u, and this is u. I don't know why I can't seem to. And this is now v and v. Where this is u plus v, and this vector is u minus v. Now we're playing fast and loose with the origin, but if you slid that tail to the origin, that is equivalent to the vector u minus v. And u plus v is easier to see. Questions on that? This is getting fun. So let's just keep going, right? Now we have all of these different relationships just based on inner products. Let's extend this idea a little bit to a set of bases or sets of bases, and in particular, let's look at vectors that are now orthonormal, orthogonal and normalized to have a length of 1. And then we'll build bases out of those. That's what we're wanting to do. So we call a list of vectors orthonormal if those vectors, if the vectors are all pairwise orthogonal and each vector has a norm of 1. That's then going to be a list of orthonormal vectors. They're pairwise orthogonal, and we know what that means. Their inner product is 0. And we know how to find the length of each vector. That's just the norm of that vector. Depending on how we define the inner product, we'll just divide by that length. So if it was of length 100, we divide it out, and now we have a vector that's of length 1. In other words, given a list, let's say E1, E2 up to E sub m, that list of vectors is orthonormal if the inner product of, let's say, E sub I with E sub j is delta sub ij, where this delta sub ij, is the Kronecker delta. That means it's 1 if the subscripts are equal and 0 otherwise. What we're meaning by that delta is delta sub ij is equal to 1 if I is equal to j and it's 0 otherwise. And the nice thing about orthonormal lists is that they're really helpful and we can build things with them. Now we have a set of sort of underlying infrastructure that we can play with a lot and really build things easily with them or more conveniently with them. These orthonormal lists are particularly useful. All right, if that's the case, then give me some propositions, some theorems, and corollaries based on these useful orthonormal lists. The first one, proposition 615. Suppose we have a list of orthonormal vectors. We're going to call those E1, E2. We have Michigan of those, E sub m. Suppose that is an orthonormal list in some vector space V. Then what we can say is that if we looked at some linear combination of those orthonormal vectors scaled by some scale amounts, and we took the norm of that vector, we can basically find that length by just looking at the magnitudes of the scale factors, if that made any sense at all. Probably not. So let me write it down. This is what I'm saying. Take a linear multiple or a scalar multiple of E1, add that to a scalar multiple of E sub 2, all the way up to some scalar multiple of E sub m. That now forms a new vector, a linear combination of these m vectors. Here the E1s are vectors. These aren't coordinates. So each E is a vector. If we now squared that, we're going to claim that that's equal to the magnitude of A1 squared plus the magnitude of A sub 2 squared. And we just keep going up to the magnitude of A sub m squared for all, let's say, A1, A2, A sub m in our field of numbers. So these E's could be really complicated, but they form an orthonormal list of vectors. And now somebody gives us a linear combination of those based on scalars that could be complex, they might be real. But they say, oh, combine those orthonormal vectors. And they say, give me the norm of that. Well, all you have to do is find the absolute value of those scaling factors, square them, add them up, and then if you needed the norm, you'd take the square root of that. If you needed the norm squared, you just leave that sum alone. And that's a lot easier than maybe computing the norm of this ugly vector and squaring it. But this provides us with a lot of useful results, but first let's go ahead and prove where that's coming from. The book just sort of says it's obvious. It sort of is once you have a good feel for it, but let's go ahead and step it through. Now the proof might be a little bit head spinning, but you just kind of need to keep your mind around it, all right? Because I'm going to use a lot of notation. First, let's start with what we have. We have A1, E1, A2, E2, plus A sub m, E sub m, the norm squared. But we now know what that is, don't we? That's an inner product of the vector with itself. It's just the vector's kind of ugly, isn't it? Well, it depends on, it's all relative, isn't it? So we shouldn't be talking about beauty here in vectors, but it's only Wednesday. But I guess this is your Friday for this class, correct? That's what I tell myself. Now you're really confused. That's the first slot. That's the vector in the first slot of the inner product. That's okay, right? And now I just have to put the same vector into the second slot. Here's where it gets a little bit interesting. But what I'm trying to do now is I'm going to pull this apart into m different pieces, m being Michigan. The first piece, I'm going to take A1, E1 and inner product it with all of these terms in the right-hand side. Then I'm going to repeat that for A sub 2, E sub 2. It needs to be inner product with everything on in the second slot. Let me show you what I'm trying to do here. The first thing I'm going to do is how many of those, if I now took the inner product of A1, E1 with all of those other pieces, what do I want to do? A sub L, E sub L, L equal 1, 2, how many of those do I have? I have Michigan of those pieces, don't I? That's now separating the inner product with A1, E1 and the second slot. And now I have to do that for each of the pieces in the first slot, meaning I now have to add to that the second piece, which is this sum from L equal 1 to m of A sub 2, E sub 2, A sub L, E sub L. And I just keep going until I run out of m's or l's. I now have A sub m, E sub m with A sub L, E sub L. Is that okay? But now I can compact that down, can't I? Because I have m of those sums. So I can now do a double summation. I can say, let me sum now over the first slot. Let me call that, oh, I guess I'll do k. K equal 1 to m, A sub k, E sub k. Whoops. Getting ahead of myself. I need to put that collection of all of these others, L equal 1 to m, A sub k, E sub k, A sub L, E sub L. Is that okay? but now what can I do? I now have a scalar in the first slot and the second slot. And we know how that slides out of each of those terms. The first A comes out unaltered. The second A, or the scalar in the second slot, comes out with a conjugate. So we can do that. We can say, well, this is the same as this sum from k equal 1 to m, sum from L equal 1 to m of a sub k, a sub L conjugate, inner product with E, K, E, L. But what do we know about the inner product of those orthonormal vectors? They're orthonormal, aren't they? So the only time you have anything that's non-zero is when these indices on those vectors are the same. This is effectively, whoops, it's looking like this delta sub KL, isn't it? And the only time that we will have that true is when K and L are equal. All the other pieces are gone. So we can look at one of these or the other. We'll just say L, since I like my L's better. We now say this is the sum from L equal 1 to M of A sub L conjugate. Because all the others go away. They were zero based on that inner product of orthonormal vectors. They're orthonormal, so the only time you get any alignment is when they are the same vector. When they're not equal, the inner product is zero by definition of them being orthogonal. And in fact, I think, didn't we call them orthonormal? So we normalize them to have a value of 1, so that's why we have that delta. But what's A sub L star? Where A sub L is a complex number. That's the magnitude of A sub L squared, isn't it? And that's what we were trying to show. So this is now just A1 magnitude squared plus, whoops, A sub 2 squared plus A sub M squared. Meaning, if we now have an orthonormal list of vectors, it doesn't have to be a basis. We could just have two vectors that are orthonormal, and we can use this proposition. Was this proposition 516? Was it? 615. Transcribe numbers. We're in chapter 6. I should have known better, right? I knew I could scroll up, but I was just checking my memory. Well, that's a scary proposition. But you have an orthonormal list of vectors. It could be 2 long, 5 long, 8 long. You know it can only be as long as the dimension of your vector space, right? Then things would start to be dependent, and they would no longer be orthogonal or orthonormal. But once you have that, then if you scale those and add them up and need to find their norm, you can just look at those scalars' absolute values and add up the square of those scalars. All right, now that we're in, it was important that I go back to find what proposition that was, because now we can start introducing all sorts of corollaries, and we can't reproduce numbers, can we? So this is now still in chapter 6, but it's the next one, corollary 616. And that one says that every orthonormal list of vectors is linearly independent. So that's why these orthonormal lists are so powerful. You give me a list of orthonormal vectors, I already know that they're linearly independent just by this corollary. Where did that come from? Remember how we would prove things being linearly independent? We would take linear combinations and find that the coefficients had to be 0 when that collection of that collection of linear vectors sum to 0. So now that's going to be our proof. We can take E1, E2, E sub m as an orthonormal list. Now let's just write a linear combination of that, but let's say that we pick A1, A2, up through A sub m, such that we get 0. But what did that last proposition tell us? Proposition 615. Hope that's right. So now the previous proposition, proposition 615, shows this means what? Remember that proposition? That said that if we started with this A1, E1, A2, E2, and A sub m, E sub m, and looked at the square of that, norm, well, we just said that that vector was equal to 0, so we really have the norm of 0. So 0 is equal to this mess norm squared. But from proposition 615, we know that that's A1 squared plus A sub 2 magnitude squared plus up to A sub m squared. But that left-hand side is equal to the right-hand side, so that sum of these scalars, absolute valued squared, has to equal 0. These have to be non-negative, don't they, if they're absolute values? We're summing a bunch of non-negative numbers and getting 0. That means none of them can be positive, can they? So they all have to be identically 0, all of those scalars, for this to be true. That means all of these A sub L's equal 0. Now if we have a linear combination of vectors that equal 0, and the only way that that's true is when the combination of those vectors are 0, then we know that those vectors had to be linearly independent. And we showed that for, that's a terrible m, but for any m. So any list of m orthonormal vectors is linearly independent. Questions on that? So now we have a orthonormal list, which is linearly independent. And when we had a list of linearly independent vectors, as long as we took enough of them, we could find a basis, couldn't we? As long as we took as many as we had the dimension of the vector space, we could find a basis. So now we're able to create orthonormal basis from these lists of orthonormal vectors. We'll pick up at that time, and what's happening next time? Nothing here, right? So stay tuned to D2L for the next lecture, but I'll see you in a week, unless I see you in office hours. But the next time I'll see you in this room is 1 week.